Hi, everybody, and welcome to section 3.2, the fundamental theorem of calculus and anti-differentiation. Anti-differentiation is the same as the integral. So we have a definition here. A function, capital F of x, is called a function, capital F of x, is called, it should be an antiderivative of the small f of x if the derivative of f of x, if the derivative of the capital F of x is equal to small f of x. Basically what that's saying is that small f of x is equal to the derivative of capital F of x. And capital F of x is the antiderivative of f of x. That's all that says. And again, just as a preview, the antiderivative will be the same as the integral, which we just learned about being the area under the curve. So the first thing it says is verify that capital F of x is equal to x squared plus 5, and capital F of x is equal to x squared minus 7 are both antiderivatives of f of x equals 2x. If we go back to what we just were learning, it says that the derivative of capital F of x is equal to small f of x. And the derivative here of capital F of x is 2x. And the same thing is true here. The derivative of capital F of x is 2x because both of those constants are going to disappear. This is what we were trying to show. So capital F of x, or x squared plus 5 and x squared minus 7 are both antiderivatives of 2x. Now again, we have a definition similar to the one we already have. Given that the derivative of capital F of x is equal to small f of x, so capital F of x is a specific antiderivative of f of x. All antiderivatives of a function only differ by a constant. We define the general antiderivative. So we define the general antiderivative of indefinite integral. I don't know what that means. All antiderivatives of a function only differ by a constant, as you saw in the last slide. So we always add a plus c whenever we integrate. And I think we've talked about this being the integral sign. All antiderivatives of a function only differ by a constant. We define the general antiderivative of indefinite integral. I don't know what that means. I'm going to get rid of it. Now we have another definition. Given that the derivative of capital F of x is equal to small f of x, so capital F of x is a specific antiderivative of f of x. Basically, we're saying here that the derivative of the function is equal to f of x, and the integral of small f of x is equal to the original function. And we'll do a lot of work with this, so don't worry. All antiderivatives of a function only differ by a constant. We saw that in the last slide. The antiderivative is also called the indefinite integral. They're exactly the same. So if somebody calls something the antiderivative, someone calls it the integral, they mean the exact same thing. We're going to start here with the power rule for antiderivatives. Remember, we had a power rule for derivatives. The power rule for derivatives was if I had a function f of x equals x to the n power, the derivative of that was nx to the n minus 1. Now we're going to do the antiderivative. Basically, what we're doing is going backwards. For example, if I started here and took the derivative of this, so I'll say the derivative of x to the n plus 1 over n plus 1, well, that's going to equal, I take the exponent and put it in the front, x to the n plus 1 minus 1 divided by n plus 1, which is equal to, well, the n plus 1's cancel, and I get x to the n because I have n plus 1 minus 1. So we can see that if we go from the function and take the derivative, we go backwards. When we integrate, we do the opposite of what we did when we differentiated. When we took the derivative, we multiplied by this exponent. Now we're dividing by the exponent by plus 1. And we add 1 instead of subtract 1. Let me say that better. When we integrate, When we differentiate, when we take the derivative, remember we move n to the front and we have x to the n minus 1. Well, this is the opposite. So instead of multiplying by n, we divide by n plus 1 and add 1. So we just do the opposite. We multiplied and subtracted 1 for the derivative. Now we're dividing and adding 1. There's one special case. That special case is n equals -1. Because if you remember, the derivative of the natural log of x was equal to 1 over x. So we have this special case where when we integrate 1 over x, we get the natural log of x. Remember, we're going backwards. And always notice we're adding c. We're adding c because the derivative of a constant is always 0, so I wouldn't know if there was some constant there before I took the before I integrate. I wouldn't know whether or not there was a constant there. There are ways, and we will learn about those, I believe. Don't worry about it. All right. More rules for integration. Similar to derivatives, if I have a function plus or minus another function and I'm integrating the entire thing, I can separate it into two separate functions, just like with derivatives. And also like derivatives, if I have a constant times a function inside the integral, I can take the constant outside the integral. So this can come out, and then I only have to worry about integrating g of x. So let's see what all that means. If I want to integrate this, I'm going to use, first, I'm going to use this rule. First, I'm going to use this rule, which says if I add or subtract two functions, I integrate each one separately. So I can say this is going to be equal to the integral of 3x squared dx minus the integral of 4x dx plus the integral of 2 dx. And I would like to point out here, since we really haven't talked about notation, I don't know if I should just talk about this. Now, if I integrate, I'm going to use two separate rules. I'm going to use one rule that we saw that said k times a function inside the integral is the same as k times the integral of the function. And I'm going to start there, and I'm going to say this is equal to 3 times the integral of x squared dx minus 4 times the integral of x dx plus 2 times the integral of dx. Now, I'm going to use the power rule. The power rule said that the integral of x to the n dx is equal to x to the n plus 1 over n plus 1, plus a constant. I can say this is equal to 3 times, I have x squared, so n is 2. This will be x to the third power over 3. And we'll add the constant at the end. Minus 4 times, here we have x to the first power, that would make this x squared over 2, plus 2, and this is really the same as 1 dx. The integral of 1 would be x. And then I'm going to put plus some constant. And each one of these doesn't need its own constant because all of them together, we don't know what any of the numbers are anyway, so I can just say there's a constant. Let's simplify this. 3 cancels with 3. I get x to the third power minus 4 cancels with 2, 2x squared plus 2x plus c. And that would be my final answer. Again, really the same thing. I'm going to start off by saying that this is equal to the integral of 5 over x dx minus the integral of 1 over x squared dx. Now, I can say this is equal to 5 times the integral of 1 over x dx minus the integral of x to the minus 2 dx. You always need those dx's. Now when I want to integrate, I get 5 times the natural log of x minus, remember my power rule says I have x to the n plus 1. If negative 2 is n, this would be negative 1 divided by negative 1 plus c. This is equal to 5 ln of x plus, because I have this minus 1, I have a minus and a minus 1. Those combine to give me a positive, and I get 1 over x plus c. And again, this would be my final answer. And if you take the derivative of this, you will get 5 over x minus 1 over x squared. The fundamental theorem of calculus. If the derivative of capital F of x equals f of x, that is that capital F of x is an antiderivative of f of x. So this is saying the derivative of the original function is f of x, And it's all, this function is the antiderivative of f of x. So they go back and forth. This is called a definite integral because we have a starting position we're starting at A and we're going to B and we're going to integrate this function. Once I integrate it, I first plug in B and then I subtract whatever the function is when I plug in A, and we'll do an example. We can use antiderivatives to evaluate definite integrals. Definite integrals meaning I will actually be able to find the area under my curve, the net area under my curve. Here we go. The area under the curve f of x is the net change of f of x from A to B. It's net because it could be positive and it could be negative. So if I were to be, let's say I was gathering information about how far I drove in a day. Well, if I started at my house and I drove to work, that would be a certain distance. Then let's say I drove from work to a restaurant. Now, if I were to integrate all this information, I would see that this part here is actually going backwards. It's going toward my house somewhat. So I'd have to subtract off some of that distance to the restaurant. Let's not do it that way. Let's say this is my house and here's my office, and I go to work and let's say it's 10 miles. On my way home, I stop and meet a friend at this restaurant, and this restaurant is 6 miles from my house. If I were to integrate over all the time from the time I left my house to the time I got to the restaurant, it would only look like I've moved 6 miles. No one would know that I went 10 miles and then back 4, unless I specifically mention that I have this negative area and I want to add it because I want my total distance that I drove, not just the distance I am now from my home. So let's evaluate this function. First thing we have to do is we have to integrate it. We can say this is equal to 6 times the integral from 1 to 3 of x squared dx. Now, I can say this is equal to 6 times x to the n plus 1, which is x to the third over n plus 1. And we're just going to add this one piece that says I'm going to evaluate it between 1 and 3. So first I integrate or take the antiderivative, and now I'm going to evaluate. This is the fundamental theorem of calculus that says when I go from a to b of f of x dx, that equals f of b minus f of a. So here I would say this is equal to 6 times 3 to the third power divided by 3 minus 6 times 1 to the third power divided by 3, which is equal to, I can cancel 2 of those, so that would be 9 times 6 is 54, minus, this is 1, 2, which equals 52. So my definite integral, or the area under this curve, is between 1 and 3 is 52. Let me draw a picture of what that would look like. First, I'm going to draw in x squared. Let's say that's x squared. Let's say this is y equals 6x squared. This is 1, and this is 3. What I just found is the area between 1 and 3 from the curve to the x-axis. And we can see that it's all positive. That's why our number is positive. So the fundamental theorem of calculus rearranged says if the derivative of capital F of x equals small f of x, or again, capital F of x is the antiderivative of f of x, small f of x, then I can say capital F of x is equal to some f of a, because I have to know where I start. That's my c. Because remember, I'm not, when I take the definite integral, I don't have to add c. But this would be adding some constant before I start integrating my function. For example, let's say I want to know the distance from my house to I want to know the distance from my house to the airport. Here's my house. Here's the airport. Problem. I wasn't home when I started figuring out how far it was. So I was here. Let's say I was at a restaurant. I can tell you what, I can find out what the distance from here to here is. I can just look at my odometer. What I don't know, and what I have to add to that, is the distance from the house to the restaurant. That would be my capital F of A. This is from the restaurant to the airport. This would be from the restaurant to the airport. That would be that distance. Now, this right here is a really handy tool. I don't think we're going to use it much in this class, but what it says is that if I take the derivative, of this function, and this function happens to be the integral This function happens to be the integral. Notice that it does exactly what inverse functions do. They cancel each other out, and I end up with f of x. The interpretation is that the derivative and the integral are inverses. Another example of an inverse, so you understand, x squared and the square root of x are inverses. If I take the square root of x and I square it, these cancel and I just get x. Similar. That's what inverse functions do. And that should take care of section 3.2. Again, thank you for watching.